Free response question number 6. The velocity of a particle, again, no calculator, moving along the x-axis is modeled by a differentiable function v, where the position x is measured in meters, time is measured in seconds. It's important to understand that this is time and this is velocity. It is not position. The position of the particle, this is extremely important. The position of the particle at x equal to 7, it is x equal to 7 when t is equal to 0 seconds. Don't forget about that important piece of information, because it's going to have an impact on questions when they ask me the position of the particle at a different time, because we're starting at 7. And again, a particle's moving, so in other words, a particle's moving along the x-axis, 1, 2, 3, 4, 5, 6, 7. And this particle is starting at 7. It's not starting at 0, and that's what they're trying to tell me right here. This is where the particle is starting. Estimate, keyword, estimate the acceleration of the particle at 36 seconds. We know that acceleration is the slope or the derivative of velocity. So since they're telling me to estimate, they're asking me to estimate using an average rate of change. And since I'm estimating at 36, well, 36 is between 32 and 40. So I'm going to go one above and one below and do average rate of change. So change in y, 7 minus negative 4 over change in x, gives me 11/8 meters per second squared. So I approximated the instant rate of change using the average rate of change. Letter B. Using correct units, explain what in the world does this mean in the context of this problem. Now, what they mean by in the context of the problem is in terms of particle movement along an x-axis. So that's the first part of the question. That's number 1. And then number 2, use a trapezoidal sum with 3 subintervals to approximate the definite integral. So let's talk about the first thing that I'm supposed to do. Explain what this represents. Well, we all know that a definite integral is an accumulator. It's totaling up stuff. And since it's velocity, when we go back, we know that this represents the displacement. That's one way to say it. Don't say position or distance. I'm sorry, don't say distance. It represents the displacement, or you could say it represents the change in position. But do not say distance, because we don't know if all the area is negative. Okay? It represents the displacement or the change in position of the particle from 20 to 40 seconds. Notice I'm being very specific and I'm using the correct units. Measured in meters, that's very important. And that's all I need to say. Now I'm going to use a trapezoidal approximation. Now the important thing to note is that if I'm going to use a trapezoidal approximation to go from 20, let me erase something up here. If I'm going to go from 20 to 40. Very important to note, let's see, I can't move this up anymore. When I think of trapezoids and I'm putting in 3, 1, 2, 3, these are not going to be equal intervals. In other words, from 20 to 25 is 5, from 25 to 32 is 7, and 32 to 40 is 8. So this is one of those cases where I have to set up a trapezoidal approximation, or I have to set up area problem for each of the 3 trapezoids. Now the area of a trapezoid, very important that you remember, 1/2 of the height multiplied by base 1 plus base 2. So notice I'm doing that for each problem. Let me pull the data back up. Okay, so it's 1/2 of 5, because 5 is the difference between the first 2 t values, and base number 1 is -10, base number 2 is -8, just straight out of the table. Then another trapezoid approximation, 1/2 of the height, base 1, base 2. 1/2 of the height, base 1, base 2. But again, what I need you to see here is that the reason I'm setting up 3 different area problems is because the subintervals or the intervals are not equal. And then it becomes an arithmetic problem, and I can see that the particle is at negative 75 meters. What were they asking me to do? Yep, a trapezoidal approximation. Okay, 6C. From 0 to 40, must the particle change direction? So we need to know, is velocity changing sign? Change direction means velocity changes sign on any of the subintervals indicated by the data in the table. If so, identify the subintervals and explain your reasoning. If not, explain why not. Well, then I'm simply going to go up to the data in the table, and what I'm looking for is in the velocity column, are we changing signs? Well, from 3 to 5, it does not appear that we are changing signs. From 5 to negative 10, well, to go from 5 to negative 10, now there could have been a sign change in here, but we can't guarantee it. But to go from positive 5 to negative 10, there had to be a sign change. To go from negative 10 to negative 8, again, there could have been a sign change, but there doesn't have to be. Same thing with negative 4. But to go from negative 4 to positive 7, there has to be a sign change. So the question is, must the particle change directions? Yes, the particle must change directions. Let's see what I wrote. It changes directions on these intervals from 8 to 20 and 32 to 40 because velocity changes sign on these intervals. Therefore, the particle must change directions. And you don't have to identify this as the intermediate value theorem, but that's really what they're testing. You may not even remember what that theorem is, but that's okay. And 6D, suppose that the acceleration of the particle is positive. Well, what does that tell me? If acceleration is positive, one thing it tells me is that the position is concave up. Explain why the position of the particle at t equal to 8 seconds must be greater than x equal to 30. All right, this is the challenge problem of this question. Now, if I'm going from 0 to 8, so on this interval right here, oh, come on. So from 0 to 8, and I'm concave up, so here's 0 to 7, here's 8. And at 0, I'm at 3, so we'll call that 3. Let's move this out of the way. And at 8, I'm at 8, I'm going to call that 8. If I'm concave up, then the implication is that the graph has to be increasing. All right, so what the heck is that going to tell me? Explain why the position of the particle must be greater than x equal to 30. Well, think about if I were going to find the area of that region using a rectangle. Remember, I can use a left endpoint approximation, a right endpoint approximation, or a midpoint approximation, but I'm trying to show that the area from 0 to 8 has to be greater than 30. So what I want to do is I want to find the smallest area that I can and show if the smallest area that I can find is less than 30, then the area has to be less than 30 because I'll be doing an under approximation. Let me show you what I'm talking about. If I were to do a left endpoint approximation, I would start right here, and that would be my rectangle that I'd be finding the area of. Now clearly that is an under approximation, but if the area of that rectangle is greater than 30, then certainly the value from 0 to 8 would have to be greater than 30. So let's take a look at that. If the acceleration from 0 to 8 is positive, then x of t, the original function, is concave up, which we talked about. X of 8, the value at 8 would be 7. Now that's where that important 7 comes from. The particle started its traveling at 7, and I need to figure out where did the particle, how much position did the particle gain from 0 to 8. So if I do what I just said, and I go back up and I do the smallest approximation that I can find, that would be a rectangle that is 8 by 3, which is 24. So I'm going to take 7 and add the 24 that I just gained and get 31. 31 is greater than 30, and since this is the smallest approximation that I could have for the area, then the actual area has to be greater than 31. I mean, has to be greater than 30, sorry.